Circuit switching is a fundamental communication technique that establishes a dedicated path, or circuit, between two devices for the duration of their communication. This circuit acts as an exclusive channel through which data flows uninterrupted, much like a dedicated phone line. Unlike other methods where data might be broken down and sent through various routes, circuit switching ensures that once a circuit is established, the entire bandwidth is reserved solely for that communication. The beauty of circuit switching lies in its simplicity. Imagine a physical wire connecting two telephones. When you make a call, a physical connection is made, and your voice travels directly to the recipient without interference. This dedicated connection ensures a constant and predictable data transmission rate, making it ideal for applications that demand real-time communication and consistent data flow. This principle extends beyond traditional telephony. Circuit switching finds applications in various domains, including data networks and even some aspects of the internet. Understanding its principles is key to grasping the foundations of modern communication systems and their evolution over time. Circuit switching operates in three distinct phases: circuit establishment, data transfer, and circuit disconnection. Each phase plays a crucial role in ensuring reliable and efficient communication between devices. During the circuit establishment phase, the network determines a path through which the data will flow. This involves reserving the necessary resources, such as bandwidth on specific links, to ensure a dedicated connection. Once the path is established, data transfer can begin. The data transfer phase is characterized by the continuous and uninterrupted flow of data between the communicating devices. Because the circuit is dedicated, there is no competition for resources, resulting in a predictable and consistent data rate. Finally, once the communication is complete, the circuit disconnection phase releases the allocated resources, making them available for other connections. This structured approach to communication ensures efficient resource utilization and guarantees a certain quality of service, making it suitable for applications that prioritize real-time interaction and consistent data delivery. The impact of circuit switching is best understood through its real-world applications. One of the most relatable examples is the traditional telephone system, which relies heavily on circuit switching principles. When you dial a number, a circuit is established between your phone and the recipient's phone, creating a dedicated path for your conversation. Another notable example is the dial-up internet, a technology that many are familiar with. Before the advent of broadband, dial-up connections used existing telephone lines to establish a circuit between a user's computer and an internet service provider. This allowed users to access the internet, albeit at much slower speeds compared to modern broadband connections. Circuit switching also finds its place in modern data centers, where high-speed optical circuits are used to connect servers and other networking equipment. This ensures low latency and high bandwidth, crucial for demanding applications like cloud computing and big data analytics. These examples demonstrate the versatility of circuit switching and its ability to adapt to different communication needs, from simple voice calls to complex data transfers in high-performance computing environments. Section 4. Multiplexing techniques, FDM and TDM. Multiplexing plays a crucial role in maximizing the utilization of a single physical link in circuit switching. Two prominent techniques, frequency division multiplexing or FDM and time division multiplexing or TDM, enable multiple signals to share the same transmission medium. FDM, as the name suggests, divides the available bandwidth into separate frequency channels, allocating one to each signal. Think of it like radio stations broadcasting on different frequencies. Each signal transmits simultaneously, but within its designated frequency range, preventing interference. TDM, on the other hand, divides the transmission time into distinct time slots and assigns each signal to a specific slot. This allows multiple signals to share the same frequency band by taking turns transmitting their data in quick succession. Imagine a round-robin discussion where each participant speaks in turn. Both FDM and TDM enhance the efficiency of circuit-switched networks by allowing a single physical link to carry multiple simultaneous communications. The choice between the two depends on factors like the characteristics of the signals being transmitted and the desired quality of service. Section 5. Advantages of circuit switching. Circuit switching offers several advantages that make it a suitable choice for specific communication needs. One of its key strengths is the guaranteed bandwidth and consistent data transmission rate. Once a circuit is established, the dedicated connection ensures that data flows without interruption or competition for resources. This predictability makes circuit switching ideal for real-time applications like voice and video calls, where even slight delays or variations in data flow can significantly impact the user experience. The dedicated nature of the circuit also enhances security by reducing the risk of eavesdropping or data interception. Furthermore, the relative simplicity of circuit switching makes it easier to implement and manage compared to other techniques like packet switching. This simplicity translates to lower processing overhead and potentially lower costs, especially for applications with predictable traffic patterns. These advantages highlight the continued relevance of circuit switching in modern communication systems, particularly in scenarios where guaranteed quality of service, security, and ease of management are paramount. Section 6. Disadvantages of circuit switching. While circuit switching offers advantages in certain scenarios, it also comes with its share of limitations. One significant drawback is the inefficient use of bandwidth, especially when handling bursty traffic. Because a circuit reserves resources for the entire duration of the communication, even during periods of inactivity, bandwidth can be wasted if data transmission is not continuous. This inefficiency becomes apparent in applications like web browsing, where data is exchanged in bursts. During idle periods, the dedicated circuit remains reserved but unused, tying up resources that could be allocated to other connections. Another limitation is the potential for congestion during the circuit establishment phase. If the network is heavily loaded, finding a free path for a new circuit can be challenging, leading to delays or even connection failures. These disadvantages highlight the limitations of circuit switching in handling dynamic traffic patterns and its susceptibility to congestion in heavily loaded networks. Understanding these limitations is crucial for making informed decisions about the suitability of circuit switching for specific applications.